Coalitional game theory is an approach to modeling strategic situations that stands in contrast to what's usually called non-cooperative game theory. And in fact, coalitional game theory is often called cooperative game theory. The names are a little misleading, and I'll get back to that in a moment, but let's first speak about what situations does coalitional game theory try to model. You may recognize these two fine-looking gentlemen. The person on the left is David Cameron, Prime Minister of Britain, and to his right, as we look at it, his left, as they sit, is Nicholas Clegg, his coalitional partner. Now, here are two political rivals who nonetheless come together, and presumably there's a reason. There's something where they can accomplish together that they cannot accomplish alone. In particular, in this case, command a majority in the parliament. And so that's a classical example where a coalition forms. In fact, we usually, when you think about coalition, we think about political parties. But coalitions form not only in politics, they certainly form in business. So the WIND coalition is the coming together of a number of firms in the United States to promote the joint agenda of wind energy, turbines and such. Again, these are companies who are competitors, and nonetheless they feel that together there are things they can do that they can't do alone. For example, lobby government, establish standards, and things of that nature. Now, coalitions aren't always among organizations or parties or firms or heavyweight things. We as individuals routinely come together to accomplish things together, whether it's to enter in marriage or, for example, build a house. When you have a carpenter, an electrician, and a painter that come together, they together can accomplish something that they can't on their own. Now, the mere fact that people come together doesn't mean that their interests are aligned or that they bring the same amount of value to the coalition they've formed. It could be, for example, that the framer of a construction crew is irreplaceable, but electricians are easy to find and one could easily replace, and presumably when they get paid for the house they build, that should be reflected in how they divide the payment. And so there's a competition of both cooperation and competition here, and so for that reason, calling these cooperative games, as the common term is a little misleading. Just as much as non-cooperative game theory is misleading as well, because, for example, if you look at a normal form game, the canonical representation of a non-cooperative game, one can easily describe a completely harmonious situation of so-called team games or common payoff games, where the interests of the agents are completely aligned. So both non-cooperative game theory and coalitional or cooperative game theory model both competition and coordination. The essential difference is the basic modeling unit. In coalitional game theory, the basic modeling unit is the group, the team, and what they can accomplish, and the analysis is based on this basic modeling.
This video is going to define coalitional games and explain what they're used for. So coalitional games, unlike the non-cooperative games that we've talked about so far, don't model individual agents taking actions. Instead, they think about groups of agents acting together. So the idea is going to be that we think about a set of agents and ask about what coalitions could form, what groups of agents could choose to work together. And to do that, we're going to define how well each different group of agents is able to do for itself. Now, in particular, in a coalitional game, we're not going to think about how the agents individually divide work up within the coalition, or how it is that they coordinate with each other in order to form a coalition. We're going to take all of that as given and instead just think about how the coalition does altogether, what kinds of payoffs they're able to achieve. We're going to begin by making an assumption that is called transferable utility. What this assumption means is that it's possible for a coalition to redistribute the value that it's able to achieve arbitrarily among its members. So, for example, if the coalition is paid its value in money, it would be possible to divide up that money and make side payments among the members in any way. In general, what this assumption amounts to is that we'll be able to assign some single value as the payoff to a coalition and trust that it can be arbitrarily divided up among the members. Under this assumption, here's how we can define a coalitional game. A coalitional game has two parts, N and V, where, as in the previous models we've thought about before, N is just a finite set of players, and we'll again index this by I when we want to talk about individual players in the set. And V kind of acts like our utility function for a coalitional game. It says for every subset of the players, S, so for every coalition S that could form, up to and including all of the players in the game, what is the payoff, V of S, that the coalition can achieve? And this, of course, will allow the coalition to divide up among its members. We'll make a normalizing assumption that the value of the empty set is 0. There are two typical questions that we want to ask using coalitional game theory, the two kind of fundamental questions. The first is, which coalition makes sense to form? Which coalition would like to form in this game? And secondly, once we know which coalition will form, how should the coalition divide its payoff amongst all of the people in the coalition? Now, we're not going to spend very much effort thinking about the first question. It's usually going to be the case that the answer is the so-called grand coalition, which means everybody. So usually all of the agents will agree to work together. However, sometimes in order to guarantee that this would be true, we have to be careful about thinking about how the coalition will divide its payoffs among its members. In particular, here's a kind of game that helps us to think about the first question. We say that a coalitional game is super additive if, for all pairs of coalitions S and T, which are both strict subsets of N, if the intersection between these two coalitions is empty, which means these two coalitions involve entirely different sets of agents, then if we make a new coalition S union T that combines these two coalitions together, the value of this larger coalition is at least as big as the sum of the values of the two coalitions independently. So, in other words, if I make a bigger coalition out of two independent coalitions, the value of that bigger coalition is always at least as big as the sum of the values that those two independent coalitions were able to get on their own. This assumption makes sense if it's possible for coalitions to always work without interfering with each other. And this is often an assumption that we make in a coalitional game. Notice that this superadditivity assumption implies that the highest payoff of all, at least the weakly highest payoff of all, is achieved by the grand coalition. So when we're thinking about a superadditive game, it's natural to think that the grand coalition would want to form. So in answer to the first of the questions that I talked about before, we're going to tend to assume that the grand coalition forms, and we're going to focus on this second question of how the coalition ought to divide its payoff. Now, it's reasonable to wonder what I mean when I say how it ought to divide its payoff. That kind of depends on what the coalition is trying to achieve. And we're going to consider two different ways of answering that question. The first is how it ought to divide its payoff if what it's concerned with is fairness. Secondly, we might Instead, wonder about how it ought to divide its payoff if what it's concerned about is stability, by which we mean everybody would be willing to form the coalition rather than instead forming smaller coalitions because they might be able to achieve higher value for themselves. And we'll look at all of this in the videos that follow.
Yeah, hi folks, this is Matt again. I am going to tell you a little bit about the Shapley value now, which is one of the most prominent ways of dividing up the value of a society, the productive value of some set of individuals among its members. And the basic idea in coalition or cooperative games in terms of trying to figure out allocating value is having some notion of what the right way to do things is, and we might say, even in quotes, say what's the fair way of a coalition to divide up its payoff. It's obviously going to depend on the way that we define fairness, and the literature has basically then taken axioms as the primary way of expressing the properties of what the desired properties are of rules for dividing up things. So what we're going to do is then have some set of axioms or properties that we want to satisfy, and then see what that gives us. The Shapley value is based on Lloyd Shapley's idea that members should basically be receiving things which are proportional to their marginal contributions. Okay, so basically we look at what does a person add when we add them to a group, and they should be getting something that reflects their added value to the society. Okay, so what's the tricky part about this? And let's just take a quick example, and that'll give us an idea of why we have to be careful in doing this. So let's suppose that everybody together in a society can generate 1, but that if we're missing any member of society, we get 0. So this is, say, a committee, and the committee all has to be present in order for it to do anything. So if it's missing any of its members, it can't just make it decide on anything. So in this situation, what do we? So we've got v of n is equal to 1, v of s is 0 if we're looking at any s that's smaller than n. So in this situation, what's true? Then the marginal contribution, if we take any individual out of this group, their marginal contribution is 1, right? So everybody is essential for generating this 1. So everybody's marginal contribution to the society without them is 1. And in this situation, we can't pay everybody what they're responsible for in terms of leading ultimately to the grand coalition. So we're going to have to think about some way of weighting contributions in order to come up with a reasonable thing. And obviously for this particular rule, it would be reasonable to add up things by 1 over n, so everybody gets 1/n of the contribution. But in situations where there's might be some asymmetries in terms of who contributes which value, we're going to have to think fairly carefully about how this should be weighted. Okay, so Shapley's axioms are going to give us a handle on this, so let's take a look at those. So the first idea is a very simple one, and one which pretty much any rule that you would think of in these settings is going to satisfy. So if we think of 2 different members of a society, say I and J, if they contribute the same thing to every possible coalition in which they could be a member, they're completely interchangeable. So that if we're looking at some coalition that has neither I nor J in it, if we add I to that coalition, we get exactly the same value as we get when we add J to that coalition. If they're interchangeable, then they should be getting out the same allocation of value. So if psi is the way that we're dividing up the value from some coalitional game, then we should be giving the same thing to I as J when they're completely interchangeable. Okay? This is a fairly uncontroversial axiom. It really captures a basic notion of fairness that if individuals are completely equivalent, they should get equivalent payments. Okay, next axiom, dummy players. So I'm sure that everyone has had some experiences with people like this. What's the idea? There's a situation where you add a person I to a coalition, and they add absolutely nothing. So no matter what S we look at, if we add I to a particular S, we get the same value as this situation without that individual. So basically, the person's completely worthless no matter what coalition we're looking at. So the idea is then the axiom is if an individual is a dummy player, then we give them nothing. Now, this is on one hand, it's a fairly reasonable axiom. If somebody's contributed absolutely nothing, there's no reason they should get anything. On the other hand, this depends very much on the perspective you're taking. So if we're thinking about a society, it could be that I contributes nothing because of reasons beyond I's control. So something happened, they had an accident, or for some particular reason, they are unable to function. Society might still want to allocate something to those individuals. So it really depends on what the time perspective is, whether we're thinking about social insurance, and so forth. But nonetheless, it's a fairly intuitive axiom, and it's going to be a fairly powerful one in what it delivers. Next one is additivity. This one is one which you might think of more about the process of allocating value. So let's suppose that we can think about looking at a cooperative game or a coalitional game, and it's one that separates very nicely into two different parts. So we can think of it as you've got one cooperative game, you've got another one, and then we think of what do you get when you sum these two things together. And the idea is that if we're looking at two different cooperative games, and then we think about what would happen if you were trying to allocate something when you summed them up, you should get the same thing from allocating one, allocating according to the second, and then adding those two things up. Okay. So the idea here is if we're looking at a cooperative game where the value for any coalition is just what it gets under the first game plus what it gets under the second game, then the way that we allocate value should be how we allocated things under the first game plus how we allocated things under the second game. So this is fairly obvious in terms of what it means mathematically. In terms of how you interpret this and what the story is for why you might desire to satisfy an axiom like this, that's a little harder. You could think of this as a story for saying, maybe society one day produces according to V1, and the next day according to V2, and if what it produces the second day doesn't depend on what it produced the first day, then we should be able to allocate the fruits of the production in the first day, and then allocate again on the second day, and those things, since they don't interact at all, we should be able to do that separately. And what an individual gets is just the sum of those two things. So you can think of a fairly logical story for this kind of axiom. Okay, so what do we get from these three axioms? The Shapley value, and let's have a look at exactly how you define the Shapley value. So the Shapley value is going to be marginal calculations. What does an individual I add to coalitions that don't have I when we add? So we've got coalition with I in it, coalition without I. We then take a peek at how much that generates. And then what we're going to be doing is weighting that by different possible ways in which we could have come up with this marginal calculation, and then dividing through by all the possible ways that we could have done this. Okay, so we'll make sure we average over all these things so that everything sums up to the full value. Okay, that's the Shapley value. We're going to dissect this in more detail in a moment. And what's the theorem? The theorem is that if we look at a coalitional game or a cooperative game, there's a unique way that divides the full payoff of the grand coalition. So if we're making sure we're dividing everything up, that satisfies symmetry, dummy, and additivity. So if you put those three axioms together, there's only one way to do it, and that way is the Shapley value. So there's a unique way which does satisfy these, and it's the Shapley value. So that's a pretty powerful theorem. There's a fairly elegant proof to this. It's fairly intuitive. We're not going to go through that in detail, but we'll go through some explanations of this. You can find the proof fairly easily in a number of different places. There's actually a nice book by Osborne and Rubenstein, for instance, which is free online, which has a proof of this. But there's a number of places where you can find this. Okay, let's have a peek at the actual value in terms of how this breaks down, and then we'll look at some examples. So what individual I is giving is, according to this formula, looks a little daunting, but the intuitions are fairly simple. So we're thinking of marginal contributions. How are they coming about? So what we're going to do is we're going to think of all the different possible ways we could build society up. So for instance, we could be building society up by first adding person 1, then adding person, say, 3, then adding person 2, right? So that would be one order in which we could build a society up. We could also have built it up by first adding person 2, then adding person 3, then adding person 1, right? So there's a whole series of different ways if we had a 3-person society that we could go about building these things up. And according to each one of these orders, we'll have different marginal contributions along the way. So here, first person 1 contributes something, then person 3 adds their production, then person 2 adds their production, and so forth. So we end up with these different contributions, and that's what this is going to capture. So what we're doing is we're looking at these different sequences, and the first part we're doing is calculating, as we went along the sequence, what did I add when they were added. Next, we weight this by the different possible ways that we could have built up the coalitions before I was added. Then we also weight this by the different orders, different ways we could add the individuals who haven't been added yet after I has been added, right? So there's a number of individuals minus the number that are already in S minus I. So that's the number of ways, the people that are still left. In fact, take that to the factorial, gives us how many different orders we can still add people in. So we weight it by that. And then we're summing over all possible coalitions that are there before I, and then we're dividing through by the total number of different orderings we could have over people in a society. Okay, so that's the Shapley value. And in terms of understanding this, again, what we could think of in terms of the ways in which we divide up a society, we can think of adding person 1 first, then 1, 2, 1, 2, 3. We could have added 1 first, then 3, 1, 2, 3. We could have added 2 first, then 1, then 3, 2 first, then 3, 3 first, then 1, 3 first, then 2, 1, 2, 3, and so forth. So we could have done this in a whole series of different orders. So there's 6 of these, right? 6 different orders. And so, for instance, if we want to figure out what person 1 adds when we add them, in the first case, this is V1. Second case, this is V1. Third case, what are they adding? They're adding V1, 2 minus V of 2 that was already there. Third case, they're getting V of 1, 2, 3 minus V of 2, 3. That's the fourth case. The fifth case, we're getting V of 1, 3 minus V of 3, and so forth, right? So we've got here V of 1, 2, 3 minus V of 2, 3. Okay, that's the Shapley value. So each one of these things is getting weighted by a sixth. Here, this turns out then to get a total weight of 1/3. Again, here we're going to get a weight of 1/3, and then these two are each getting a weight of 1/6 each, right? So that gives us the total value of the Shapley value, and that tells us what person 1 should be getting in this setting. Let's take a look at a simpler example just with 2 individuals and try and figure out exactly what the Shapley value gets. So these are 2 people, they form a partnership. So person 1 alone was generating production of 1. Person 2 was generating a production of 2. They say, wow, let's get together and form a partnership. We can do better than we can separately. They generate a total value of 4. So this is nicely super additive. We're getting a higher value when we've got the 2 together. And now they sort of, at the end, they try and say, okay, well, how should we divide the 4 among them? Well, in this case, we could have added 1 first and then come up with 1, 2. The other possibility is we get 2 first and then 1, 2, right? So there's only 2 different ways we could have built society up. So person 1 in the first, if we're trying to figure out what to give person 1 out of this, here they would get V1, right, which is 1. Here they would get V1, 2 minus v of 2, the marginal contribution they added if they were added second. This is the marginal contribution if they were added first. What's this value? This value is 2, and each one of these gets a weight ultimately of 1/2, because we've got 2 of these things. So we're adding a half of 1, a half of 2. We get 1.5 is equal to phi of 1. You can go through, you can check that 2.5 then is going to be equal to phi of 2. So here, what do we end up with? The Shapley value gives us that if these are the contributions that people were making, you're going to end up with 1.5 as the right amount to give to person 1 and 2.5 to give to person 2. Okay? So they're each, in this case, getting some value that depends on so it's taking into account what these values are in trying to divide the 4. So they don't just say, okay, let's just split the 4 50-50. They're doing a different calculation than that. And comes out at 1.5 and 2.5 in this case. Okay, so what about the Shapley value? It allocates the value of a group according to marginal calculations. It's captured by some very simple logic and axioms. And what you could do is you can think of other axioms. You could think of other ways, other fairness ideas, or other kinds of things that you desire your rule to satisfy, and that's going to come up and make different kinds of predictions. And we'll take a look at the core next, which is uses a different kind of logic than the Shapley value for making predictions about how a society should divide up its values.